Alright, if you haven't watched the previous video where we talked about dy problems, I'd highly encourage you to watch that because I actually got quite a bit into this topic already in that video. So basically it's going to turn out that any problem technically can be worked with either dx or dy, meaning either vertical, which would have dx, or horizontal, little representative rectangles, which would be dy's. But each particular problem, or each particular region, like depending on which curves and everything they give you to find the area between, the different curves will favor either dx or dy to make them simpler. Other times the teacher will just tell you flat out, hey, I want you to do this in dy. Or if you're in the volume chapter, which is coming up next, they might make you use the shell method or make you use the disk method or something, and that can sort of be a backhanded way of forcing you to use either dx or dy. So that's why we need to practice it and get good at it. But on these problems, a lot of times you'll have the choice, and the question is, which one do I use, the dx or dy? So depending on the region, one might be better than the other. If you look at this region on top, so this region on the left, dy or dx will work. Now, I mentioned this quite a bit in the last video, but when you find the area between two curves, or even just when you find area using integrals, definite integrals, what you're really doing is a Riemann sum with infinity little rectangles. So the magic of the definite integral from a to b is, you know how we did Riemann sums where you could sort of put 5 rectangles under a curve and kind of ballpark the area? Well, it turns out when you integrate a function, it's sort of automatically, I mean, the magic of this thing is that it's automatically doing infinity rectangles, which is obviously going to be more accurate than 5 rectangles, right? So this is perfectly accurate. What it's really doing is sort of creating and adding up. Infinity rectangles are extremely skinny. When we do vertical rectangles, this is just one of my infinity rectangles I just drew for reference, but there'd be a rectangle here, 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 here. They're going to start back at this little corner, get longer and longer, eventually fill in this entire region with a bunch of vertical, extremely skinny rectangles. How skinny are they? They're dx wide, and dx is like really close to 0. So when we do dx integrals, we're adding up vertical representative rectangles. But when we do dy problems, and this one down here would be a dy problem, we're adding up horizontal representative rectangles, which have a thickness of dy. So dy is this skinny, skinny width, like hair's width, of a horizontal rectangle. So your rectangle is kind of long and skinny to the left and right, but it's extremely thin. You can see how that distance is a vertical distance. Like if you measured the right-hand edge of a little rectangle, this right here is a y distance. It's sort of a vertical distance. And that's why we're using dy for horizontal rectangles. So it's kind of backwards. If your rectangle is vertical, i.e. parallel to the y-axis, you're actually using dx. And if your little rectangle is sideways, parallel to the x-axis, its thickness is dy. So that's a little bit backwards from how you might expect it. But the moral of the story is that if you look, like you look at this downstairs, this region right here at on the bottom chart, these are horizontal rectangles, and the reason I know they should be horizontal is because as I work my way across this region, each one of these rectangles, one end is on this parabola, and the other end is on this line. So it's just a one-shot integral. That's really great. If I had tried to integrate this same region with vertical bars, then some of the ones, when I start here on the left, you'll notice that both ends of these little rectangles would be on the parabola. But then as soon as I work from left to right, once I get to x equals whatever this is, the top end of my little rectangles are still on this parabola right here, but the bottom end of the little rectangles is now on this line, which means I'd have to integrate twice. I'd have to make an integral covering this range of x. So that's integral 1. And then I'd have to do a separate integral to get the area of this right half over here. So that's integral 2 from x equals this to x equals this. So that's why that's a bummer. This region down below, I want to use horizontal bars. This region right here, opposite problem. If I did this with horizontal bars, then some of the bars are going to have one end on the parabola, one end on the line, but some of the other bars are going to have both ends on the parabola. So that means I'm going to have to break into 2 dy integrals if I wanted to use dy. I'd have to integrate between these two curves, between the line and the parabola to get this region. I'd have to integrate from one side of the parabola to the other to get this downstairs region, the bottom half. But if I use vertical bars instead, see how if I just draw vertical bars, I can go all the way across the region and never have to draw a bar that doesn't go between the, every single one of these bars goes from the parabola on the bottom edge to the line on the top edge. So that's what I'm looking to do. I'm looking to see whether it's either verticals or horizontals that would allow me to do it in one integral And this is actually exactly what's going to happen in the volume problems with the disk method and washer method and shell method. What you're going to do first, if you're ever debating whether to use shell method or washer method, the first thing you'll do is sketch the region and try and figure out whether vertical bars or horizontal bars are better. And then you'll pick the method that corresponds to that orientation of bar, either dx or dy, and the spin axis. So we'll obviously wait to get into that for next chapter. But the point is that analyzing the region and figuring out whether you want to do horizontal dy bars or vertical dx bars is going to be the first step in your area problems and also your volume problems. All right, so graph first. That's my point, and then decide. So x equals y squared. We already saw that that looks kind of like this. And negative x plus 2. So that's going to be a y-intercept of 2. Then negative x is sloped like this. All right, so there's a point of intersection. So we must be talking about this region here that's got a parabola on the left and line on the right. Now we can do the experiment. We can look and say, hey, do I want to use vertical bars or horizontal bars, rectangles, to calculate this? If I do vertical bars, this left section has both ends of the bar are on the parabola, and then this right half, we'd have one end on the parabola, one end on the line. So vertical bars would require two separate integrals. The one from 0 to 1, which is right here, and then the one from 1 to whatever this number is. So this is a problem where I'm going to want to use horizontal bars, because if I do horizontal rectangles, no matter any horizontal rectangle I draw in here, they always have one end on the line, one end on the parabola, so it makes it a simpler integration just with one integral. All right, so now I've decided I want to do dy, because horizontal bars means dy. So I want to integrate in terms of dy. So now I need to start figuring out some stuff. I need to figure out what the two equations are, and then I need to figure out the limits of integration. The equations are actually pretty simple. So my right-hand one, I've got one function in terms of y, but the other one's in terms of x. So I need to rearrange this equation to get it in terms of, x is a function of y. So I need to get x by itself, basically. So I got y minus 2 equals negative x, which means that x equals 2 minus y. All right, so x equals 2 minus y is just the algebraic rearrangement of this, solving for x. And that is my right-hand curve. So my first function is 2 minus y. I'll be subtracting the left one, which is just the parabola. All right, so there's my integral. Now I just need my limits of integration to figure this out. So I just need the range of y values. I need to know the y-coordinate at this point and the y-coordinate at this point, because this is sort of like the highest point up in this region, and this point is the lowest. So I just need to figure out what that y value is and what this y value is, and I'll be set. So you could set them equal to each other and solve. Yeah, why not? So we'll just set y squared, basically set these two things equal to each other. So we'll set y squared equal to 2 minus y. So it looks like a factoring situation. Just got y squared plus y minus 2 equals 0. Remember, the first step to factoring is put everything together on one side, set it equal to 0. This factor is to y plus 2 and y minus 1. So that means negative 2 and positive 1 are the two y coordinates at which things would intersect. Now I could go through and find out the exact coordinates at this point, but it doesn't really matter. The y coordinate is all that matters, because that's my negative 2, my 1 are the limits of integration. So let's do it. Looks like this thing is pretty much ready to integrate, because I don't have to distribute any negatives or anything that would mess me up. So integral of 2 is 2y. Integral of negative y is negative 1/2 y squared. And integral of negative y squared is negative 1/3 y cubed. And this, of course, is from negative 2 to 1. All right, this is going to be a mess, so let's just be careful plugging in. When I plug in 1, all the y's basically are just 1, so I just get my coefficients. So that's 2 minus 1/2 minus 1/3. Now I get subtract, plugging in my lower limit. So if I plug in negative 2 here, I get negative 4. Negative 2 squared is positive 4 times negative 1/2 is negative 2. And then plug in negative 2 to y here is negative 8 times negative 1/3 is positive 8/3. All right, what a mess. So if I distribute this negative in, that cancels these negatives, but this becomes negative. All right, so now I just got a lot of numbers to combine. Let's do whole numbers first. That's how I like to do it. So I got a 2 plus 4 is 6 plus 2 is 8. Now I got some thirds. I got a negative 1/3 and negative 8/3 for a total of negative 9/3. And then I've just got a negative 1/2. 9/3 is just 3, so I got 8 minus 3. That's 1/2, which is 8 minus 3 is 5. That's 1/2, which is 4.5 or 9/2, whichever way you like to do it. All right, so you can see that just to ballpark what just happened here, we had a choice of using either horizontal or vertical bars. And we realized that if we did vertical bars, both ends, at one point, both ends of the bar, the upper function and lower function would both be defined by the parabola on the left half of the region, but then we would switch to the area where all the bars are defined by both the line and the parabola. So we'd have two separate integrals. That would have been a mess. Just for kicks, I'm just going to show you we could have done that. I'm not going to actually execute the integral because it's kind of a painful one, but if x equals, so first thing we need to do is look at the limits of integration. Looks like x would go from 0 to 4. So if you plug in negative 2 to the original function, you get 4 for x. So we're going to integrate from 0 to 4. Well, actually that's not true. First I got to do the left region. So just this left region, just this portion, is from 0 to 1. And that's going to be the top curve, which is square root of x. Because remember, if x equals y squared, that means that y equals plus or minus square root of x. Positive root x is the upper portion of the parabola. Negative root x is the bottom half. So if I want to, so my upper curve is positive root x, my bottom curve is negative root x. This is the top curve. This is the bottom curve. But then of course the negatives cancel, so I just get x plus root x. All right, so that's for the left-hand portion, but then the rest of it from sort of x equals 1 to x equals 4. Now my top curve is the line, which is negative x plus 2. And my bottom curve is the negative root x. All right, so obviously these root x's would add up to 2 root x. Over here, these cancel. But if you're just looking at this, you notice a couple of things. Now I have two integrals to worry about with two separate sets of limits of integration. So even if I got this far correctly, which is a long shot, right, because that was pretty tricky what I just did, the other problem I've got is there's going to be so much algebra in executing these integrals and plugging in all these different limits of integration. I got roots multiple places. So this is like a hard thing to plug and chug through. Whereas on this one, no fractional powers, no roots to worry about. It was much more straightforward. That's why you want to look at the region and figure out which way is easier. Which way allows you to only do one set of integration. And in this case, it was horizontal bars, which meant we wanted to do dy. All right, let's take a look at another one. Find the area bounded by x plus 1 squared. So that is a parabola that's left shifted 1, because you do the opposite of whatever number's in here with the parentheses. So it's left shifted 1. And see, that's going to go through 1, 1, I think. Once you graph enough parabolas in your life, you start getting a feel for where the points are. Then we got y equals 2x plus 5. So positive 5, 1, 2, 3, 4, 5 is the y-intercept, and it has a slope of 2. So all right, it looks like we have set these equal and solve for that point, but looks like we got negative 2 comma 1 as this point. And then the other place they intersect is, boy, I don't even know. I'm going to guess 3. X equals 3. Or sorry, x equals 2. 2 plus 1 is 9. So I think this is probably 1 comma 9. No, 2 comma 9. I just said right. Let's just double check that that works for both. If I plug in 2 to this equation, I get 9. If I plug in 2 to this equation, I get 9 also. Okay, so 2 comma 9 and negative 2 comma 1 are 2 points. We also could have solved for those algebraically, but we'd have to FOIL out the x plus 1. We'd set x plus 1 squared equal to 2x plus 5. Then we'd FOIL it out, solve for x. It takes a while. All right, so there's our region. So once again, we're faced with a region where either dx or dy is going to be easier. If I draw horizontal bars, this is not the way to do it, because in the upper portion of the region, the left would be defined by the straight line, the right would be defined by the parabola. But then as soon as I got below into this area of the curve of the region, both ends of the rectangle are resting on that parabola. That's the problem. I'd have to split, if I do horizontal rectangles, I'd have to split my region into two. I didn't have to integrate from y equals 0 to y equals 1, then from 1 to 9. If I do vertical bars, in contrast, much better. Every bar I can draw is always going to have one end on the line and one end on the parabola. So that means I can just integrate in one fell swoop from -2, the leftmost corner of the region, to the rightmost, which is +2. Now I just need, and this is dx, right? So if I'm doing vertical bars, their width is actually dx in the x direction. Or just think of it as opposite. If vertical bars, which you'd think would be y, are actually dx, because their width is in the x direction. So I've got a dx. X is going from -2 to 2. Remember, it's whatever letter is here, that's what gives you your limits of integration. So since we're doing dx, that means that we need the x range of the region. And then my top function is the 2x plus 5. And then my bottom function is x plus 1 squared. Put that all in parentheses to multiply by dx. Alright, so at this point we're good to go. It's just going to be some algebra between here and there, because I'd like to, I could technically integrate this right now using the power rule and stuff, but it's easier if you just FOIL this out and simplify. So 2x plus 5 minus x plus 1 squared is x squared plus 2x plus 1. Alright, so if I combine like terms here, distribute this negative, so that's integral from -2 to 2 of 2x plus 5 minus x squared. Now remember, this negative sign, it's in every problem, and that's a really good way to make a mistake. So we're just going to do an extra step where we just distribute that negative in. Alright, so 2x minus 2x, cool, those cancel. So we got 5 minus 1 is 4. Combine the 5 and -1, we get 4 minus x squared dx. Alright. Pretty cool, I guess. So now we just integrate, so we get 4x minus 1/3 x cubed from -2 to 2. Alright, we plug in 2, we get 4 times 2 is 8. Minus 8/3. Boy, that 8/3 comes up a lot, doesn't it? That's because basically every time you integrate a parabola, you end up with something like that. So that was our top limit integration. Now we got to plug in -2. So 4 times -2 is -8. And then, see, we got -1/3 times -8. Because -2 cubed is -8 times -1/3 is positive 8/3. Here's yet another negative that has to get distributed in. So negative times negative is positive, and then that makes that negative. Alright, so we got 8 plus 8 is 16. And then we got -8/3 minus 8/3 is minus 16/3. Where have I seen this before? 48/3 minus 16/3 equals 32/3. Now the reason that looks familiar is the previous problem, I did the same reason but on its side. Instead of, or it was very similar, I should say. But it was a sideways problem, but basically I just took the region and flipped it sideways, but it was a very similar region, so we got the same area. Alright, pretty cool stuff. Awesome. Alright, why does this problem say, what about U substitution? I don't know, let's find out. Alright, so we got the area bounded by this and this. Let's graph them. What does the graph of this thing look like? I have no idea, so I'm going to start plugging in points. It's a function in terms of y, so I got to plug in y's to get x's. So if I plug in 0 for y, I get 0. I get -1 squared is 1 times 1/3, so I got 0, 1/3. Then if I plug in 0, oh, that was 0 for y. Got 1/3 for x. If I plug in -2 for y, I get -3 squared is 9. 9 times 1/3 is 3. So I got -2, 1, 2, 3. Alright, where's the vertex on this thing? If I plug in y equals 1, I get 1 minus 1 is 0. Okay, there we go. And if I plug in y equals +4, let's say, 4 minus 1 is 3, 3 squared is 9, 9 times 1/3 is 3. Alright, So that 1/3 kind of messes with us. It makes the whole numbers hard to come by. But the real point is I've got 3 comma 3. Sorry, that was 4. So I got 3 comma 4, and I've got 3 comma negative 2, and I've got my vertex. Now I knew this was a parabola because it had a squared in it, right? And I knew it was a sideways parabola because it had the y was the squared thing, not the x. And this is 0 comma 1. All right, so that's I got a kind of weird sideways parabola here that's doing some funky stuff. And let's see what else we got. So for our other curve, we got a line with a y-intercept of 1, so that goes through right here, and then a slope of 1. So this is actually going to go up 1 over 1, up 1 over 1. Does a point comma 3 comma 4 work for this? 3 comma 4. Yeah, so actually this is the other intercept. So the two curves, it's just a line and a parabola that intersect right there at 3 comma 4. And is y equals x plus 1. All right, so we've got our two curves. Now the question is, do I want to use dx or dy? I personally would normally want to use dy, or dx, sorry, because you know everyone likes using dx better. But the problem is that I've got this thing already in terms of y. So let's go ahead and use everything in terms of y. That means I need to rearrange this as x equals y minus 1. So I've got an integral. If I'm using dy, I need the y region, which goes from y equals 1 to y equals 4. And my top curve is the crazy one, so 1/3 times y minus 1 squared minus the bottom thing, which is x plus 1. All right, so it turns out we don't actually need the chain rule because y minus 1, if you set u equals y minus 1, your du is just dy. Because there's nothing in front of that y, it actually doesn't need the chain rule. But that doesn't mean it was a bad idea to check. If this had been 1 minus y, all of a sudden a negative sign would be involved. All right, so this just integrates pretty straightforwardly. Oops, I meant y plus. Sorry, we needed this version, which is y minus 1. So I'll just rewrite this a little bit. So 1/3 y minus 1. Now let's distribute in this negative sign to make our lives a little bit easier. All right, so now I can integrate. So I've got 1/3. Now I got to do a power rule on this y minus 1, so that's going to be, its new power is 3, so that's times another third, y minus 1 cubed, minus 1/2 y squared plus y, and that's evaluated from 1 to 4. All right, so we got 1/9 times y minus 1 cubed minus 1/2 y squared plus y. 1 to 4. So let's get going. So we got 1/9. If we plug in our upper limit, which is 4, we've got 4 minus 1 is 3. 3 cubed is 27. 27 over, so that's 27 times 1/9. Minus 1/2 times 4 squared, which is 16. Plus y, which is 4. All right, so that's just my upper limit of integration. Then I got to take away, plugging in the lower limit, which is 1. If you plug in 1, you get 1 minus 1 is 0, so that first term goes away. Then you got negative 1/2 plus 1. All right, so if we distribute in this negative, that ends up canceling that and making this negative. Okay, so I need to actually start working up here. I ran out of space. I know that happens to you guys all the time. So 1/9 times 27 is 3. 1/2 times 16 is 8. Then I got plus 4, plus 1/2, and minus 1. All right, so if I combine all this stuff, I got 3 minus 8 is negative 5. Negative 5 plus 4 is 1. That's not right. 3 minus 8 is negative 5. Negative 5 plus 4 is negative 1. Minus 1 is negative 2. plus 1/2 equals negative 3/2. All right, what happened? What went wrong? Right away, what I want you to do when you get in the same situation, and I actually did this on purpose to show you guys what happens. The negative 3/2, whenever you get a negative area, you should just be thinking, oh, I must have switched things. The area is actually 3/2, but it's a positive 3/2. So look at where the error came in. Back here, I carelessly put the left curve first, because remember, I always want to take the right-hand curve minus the left curve when I'm working with dy's. Sort of the more positive curve minus the more negative curve. So the one that's on the sort of in the positive x direction, the top curve, if you will, is actually the one that's on the sort of the bottom. It's this one. So I actually needed to do y minus 1. The correct integral would have been from 1 to 4 of y minus 1 minus 1/3 y minus 1 squared dy. So you see I just mixed up the order of these two. And by switching left and right, that switched my minus signs, and that's why I ended up with negative 3/2 instead of positive 3/2. But I would encourage you, these problems are hard enough, you're not going to have a lot of time on a test to rework them. So if you get in trouble like that, really good chance that you just switched the order, and you can just switch the sign on your answer and you're done. Of course, if you had time, you could also, obviously go back and rework it and switch minus signs throughout the problem. But there's probably going to be some fudging involved of just like switching the sign, or you won't be able to get it right. All right, on this one, we're going to use dx and dy to get the area of the region. I did this a bunch of times in the last video too. So we've got x equals y squared, our favorite sideways parabola, and x equals 4. 1, 2, 3, 4. All right, so here's my region from 4, 2. Then we got the bottom half too, because you know it's x equals y squared, so we actually have to go down to here, which is 4, negative 2. Just remember, x equals y squared is both the top and bottom. So we want to find the region, this whole region. So if I work this in terms of x, this is going to be the integral. The top curve is going to be root x, and the bottom curve is going to be negative root x. Because when you solve this equation for y rather, you have to take the square root of both sides to get a plus or minus root x. So this is going to be the integral. If I'm integrating with vertical bars, that's a dx situation. So it's going to be the top function, which is root x, minus, and then the bottom function is negative root x, from 0 to 4 is the span of x values covered by this region. All right, so that's going to equal the integral from 0 to 4 of 2x to the 1/2 dx, which equals our new power. So we got the 2, then our new power is x to the 3/2, which means we got it times the 2/3, x to 3/2, by over from 0 to 4. So 4/3 times, if you plug in the top limit, you get 4 to the 3/2 is 8, because you square root 4 and then cube it. So we'll get 8. And then you subtract 4/3, plugging in the bottom limit, which is 0, and that's just 0. So all this goes away, and we get 32/3. All right, so that was fun. We had to convert this x equals y squared into a function of y, which is root x and negative root x, in order to use the dx scenario. But we got 32/3. Let's see if we get the same thing in terms of y. So now we'll integrate the whole thing in terms of y. This one should be a little simpler. The y dimension of the region is from negative 2 to positive 2. Those are my maxima and minima of y within this region. So negative 2 to 2. The right-hand curve is just the flat line. That's just the curve x equals 4. And then the right-hand curve, or the left-hand curve, is just y squared. So you can see there's actually a little bit simpler integral to execute on. All right, so 4 times 2 is 8, minus 8/3. And then we're going to subtract, plug in the lower limit. So then I got a negative 8, and negative 2 cubed is negative 8 times negative 1/3 is positive 8/3. All right, so once again, I got to distribute in this negative sign, which happens a lot in calculus. So that would cancel this to a positive and this to a negative. So I'm going to get 16 minus 16 thirds, which equals 32 thirds. Oh, look at that. We got the same thing. So two very different looking integrals. This integral had a y squared in it. This had square roots in it. And yet we ended up with the same number. Pretty amazing. Makes you think that this method probably works. We're not just whistling Dixie here, to coin a phrase. All right, so these are vicious boogers. But as you can see, if you just look at the region first and decide whether horizontal or vertical bars are easier for that particular region, don't let your bias get in the way. Get sort of adept, like practice enough that both dx and dy are doable for you. And then, so that when you look at a region, you can just sort of be agnostic and say, you know what, is this a better dx region or a dy region, and then just execute the one that works better for the region. And that's going to help you a lot when you get into volumes, which when you're looking at shell method versus washer method, the real choice is whether each given region that they're telling you to revolve is a better for a dx problem or a dy problem, and that's going to dictate to you whether you can use the shell method or the washer method. So depending on how hard your class is, if you're in an AP class, you really need to be good at both shell and washer. So it's really going to be all about looking at that region and deciding which one is easier to do. If you're in an easier class, it's going to be more like they'll mostly give you regions that work better for one or the other. But either way, if you're finding the area between curves, analyze the region first and then pick a dy or dx second.